We next consider the power flow along the z direction. To find out the power density along z, we start from the time averaging Poynting vector. By using PAV.z hat, we can obtain the power density along the z direction, and take the definition of the time averaging Poynting vector we can have. The power flow along the z direction can then be expressed as in this way. And for t wave, consider the E close H, the direction of E close H conjugate. We just want to have the z component. As a result, we can re-express this expression as it will become minus half real part EY times HS conjugate. And we have obtained the E field and the H field in median 1, right? So take the EH field in median 1 into here, then we will have we have the result shown here. Okay, then let's do some arrangement for this long term. For the first term here, we can rewrite it as we can rewrite it in this way. And clearly you know that this term stands for the reflection coefficient, which is the amplitude of the reflected wave over the amplitude of the incident wave. And the second term here can be also rearranged in the same way. And we have conjugate here, so we write it in with a conjugate. Okay, then this term and this term, they can be re-expressed as these two. So take these two into here and here, you can obtain Okay, and as I have said, this one is gamma and this one is also gamma. So we can express these two by using these two and have this one. And due to the z sub 01 is a real number, so the conjugate of the z sub 01 is still a real number. So you can take it here. And after you multiply these two and perform the real part, you will have the power density along the z direction can be obtained in the final form like this. And clearly, this part is the incident power density. Okay, this part is the incident power density. So this one means the transmitted power. Okay, so this one means the averaging. Transmitted power. So from this definition and from this part is the input power, we can know that this part will be the reflection, power reflection. We call it okay. Remember that gamma is the reflection coefficient, but the square of the absolute value of gamma means the power reflection. They are different, okay? And the figure shown in the right hand side is an example for the TE plane wave incident to the interface formed by two materials with the index of 1 and 1.52. That is, we have a dielectric interface here, plane dielectric interface. And in the above is material with index is 1. And then here is the index of 1.52. And we have the normal vector defined as this. And the incident angle theta is defined in this way. So along this axis is the incident angle theta 1. And along this axis is the power reflection, the square of the absolute value of gamma. So this blue curve show you the power reflection of TE wave to this plane dielectric interface. And from this curve you can see that first, theta 1 is increased. You can see the power reflection is also increased. Okay? Besides, you can find out that for TE wave here, there is no situation for the power reflection is 0. This means that no matter the incident angle is, you always have the reflection for TE wave incident to the plane dielectric interface.